Let me start with biomolecules today. Biomolecules mainly has four parts. The main compounds of biomolecules includes carbohydrates, then nucleic acids, then amino acids, lipids, hormones, fats, and uh, vitamins. These are all small parts. The main part of this topic is about carbohydrates and amino acids. Carbohydrates, the old definition was hydrates of carbon, which means if you have some X number of carbons and some Y ratio of water molecules with it, that composition is called as carbohydrates. And that was pretty much good match for molecules like glucose, fructose, sucrose, and so on. But on the other hand, that definition is also matching for acetic acid, which is also C2 and H2O twice. And it is also matching for formaldehyde, which is C1 and H2O1. And this is not a carbohydrate. So that's when the definition, if you notice, there are certain cases where they are actually carbohydrate by nature, but they do not have this kind of ratio satisfied. So it is not necessary that if there is a ratio, they have to be carbohydrates, or if there is no ratio, they may still be carbohydrates. Okay. So the definition was later changed, and now the actual definition is optically active polyhydroxyaldehydes are ketones. And this optically active is also not for every case. Okay. So for some cases, optically activity may not be there. Still, we call them as carbohydrates. But the most important condition for carbohydrate is we must have a polyhydroxyaldehydes or ketones. Okay. Now, this might be in the form of a dimer. They might be in the form of a polymer also. And if these dimers and polymers on hydrolysis, if we are getting a polyhydroxyaldehydes or polyhydroxyketones, even then we can call them as carbohydrates. Okay. The two main carbohydrates that we need to know are, that we have to know much more in depth is about glucose and fructose. Okay. By molecular formula, glucose is C6H12O6, and same goes with fructose also, C6H12O6. Correct. While glucose has an aldehyde group, fructose has a keto group. Okay. Okay. So glucose has aldehyde and fructose has keto form. Clear? And when it comes to glucose, here you can see we have OH, 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 and OH. So there are how many? Five hydroxy groups. So hydroxy, five hydroxy groups. Five hydroxy groups. Got it? And you can see there is one aldehyde group. Okay. Now, this is designated as D-glucose and its mirror image is going to be L-glucose. Now, the D-glucose is with respect to this particular chiral carbon here. So, you can see the one which I'm marking. On this chiral carbon, if I write the Fisher, when we write the Fisher projection of glucose, this is a Fisher projection of glucose, on which if the fifth carbon, so let me put the numbering also. So 1, 2, 3, 4, 5, 6. If on the fifth carbon, if you notice the OH is on the right hand side, then we usually call it as capital D glucose. Okay. And if the OH is on the left hand side, we call it as capital L sugar. So in this case, it is glucose, so it is L sugar. Okay. So this is a D sugar and L sugar. While the glucose is also identified as dextrorotatory. Okay. Dextrorotatory. Dextrorotatory means, dextrorotatory means, dextrorotatory means this molecule, uh, if you take it in a pure form, it will give you a positive rotation or a clockwise rotation on the polarimeter, while the L-glucose will be levorotatory. So I can write a plus sign here showcasing that it is dextro and levo. So remember, this D and L does not represent dextro and levo. They are just labeling about a family name. This is like a family name, just like I would have a surname like K, so you might have certain surnames. So similarly, this glucose is like a D glucose, this is like an L glucose. And it is a coincidence that it is also a dextrorotatory and this is levorotatory. Got it? Clear? But that has nothing to do with capital D and capital L representation. Okay. The angle of rotation approximately is found to be 57.2 degrees on the polarimeter plus 1. Okay. And whatever I'm writing, this is all about D glucose I'm writing. I'm not writing about L glucose. L glucose is just to show you that it is a mirror image. Got it? Okay. So this is all about D glucose sugar. And now notice we have on second position, third position, fourth position, fifth position, there are chiral centers. So there are four chiral centers. On total, we have four chiral centers here, correct? So if you have four chiral centers, if you have to write the IUPAC name for glucose, what would that be? The IUPAC name would be like this. See, on the second position, the rotation is actually when you put it on the CIP rules, when you put the CIP rules, you will notice that this carbon is actually R rotatory. This one is S rotatory. This one is again R rotatory, R rotatory. So we will have something like 2R, sorry, yeah, 2R, 3S, 4R, 5R, like this. And then we have 2 comma 3 comma 4 comma 5 comma 6 pentahydroxy, pentahydroxy, okay, hexanal, pentahydroxy hexanal. This is the IUPAC name of the glucose, the dextroglucose. Clear? So if you change the configuration, then that will become L glucose. Okay. So next, notice about fructose. Fructose is a keto group. Okay. So if you notice here, we have actually three chiral centers on the Fischer projection. Got it? So basically, it has five OH groups here. We have five OH groups and one keto group. One keto group. Now, when it comes to D-glucose, right? D-glucose was identified as a levorotatory. Okay, so I will write this as D-fructose. Sorry, I'm talking about fructose. D-fructose is identified as levorotatory. Levorotatory. Okay, that means minus. Okay, the angle of rotation was found out to be minus 92.7 degrees. It's not that you have to mug up, just need to know that it is negative angle. And there are three chiral centers on fructose. Okay, this is what we need to know. Clear? So similarly, if at all I have to write the IUPAC name for fructose, so what would be the IUPAC name here? This is 3S, 4R, 5R, and then we have 1 comma 1 comma 3 comma 1 comma 3 comma 4 comma 5 comma 6, 5 comma 6, and this is pentahydroxy, pentahydroxy, okay, hexane, hexane 2 one, hexane 2 one. So that is the name for fructose. Got it? This is the name for fructose. Please check. So first I want you to, make sure that you get very comfortable with the information of glucose and fructose. Okay, this is kind of a basic requirement for this topic. Okay, so before we dig into classification of carbohydrates and everything, how to write the Fischer projection, first thing first, just know more details about glucose and fructose. All right, please check quickly. Check out the brief information about sucrose also. Okay, sucrose is also known as inward sugar. Inward sugar. Sorry. Its molecular formula is almost like a double of glucose without water molecule. And when you add that water molecule in acidic medium, it will convert into C6 H12O6, which is glucose, and another C6 H12O6. This one is fructose. Got it? Now, originally this is a dextro rotation. Sucrose is a dextro rotation, and then after it becomes glucose and fructose, here it will become dextro rotation. This will be dextro rotatory of 52.7 degrees. This is levo rotatory of minus 92.7 degrees. And now if you add both of them, overall it gets negative value, right? That is the reason why originally it was supposed to be dextro, but now after adding water, now the overall solution shows levo, because you can see the overall solution has more levo than dextro. That's the reason why we call it as invert sugar. Okay, this is another important information about sucrose. Clear? Now let's see how do we classify the carbohydrates. First, on the basis, a general term is whenever you have any sugar units, we call it as saccharides. And if you have one unit of sugar, we call it as monosaccharide. One unit, how do we decide it is one unit? That means this is a unit which cannot be further hydrolyzed into smaller units. And they are generally very sweet in taste. They are water soluble. For example, glucose, fructose, mannose, galactose, ribose, all of these are uh, monosaccharides. Okay. Oligosaccharides. Oligosaccharides are those which on hydrolysis will give 2 to 10 monosaccharides. Okay. They are also generally sweet in taste and water soluble. For example, sucrose. Sucrose is a uh, oligosaccharide or a disaccharide which will convert on hydrolysis will give you glucose and fructose. Lactose will give you glucose and galactose. Maltose will give you glucose and glucose. Okay. So if you get any number of units, these are called 2 to 10 of any 2 to 10 values, then we call them as oligosaccharides. So these are all oligosaccharides. Next, what are polysaccharides? If on hydrolysis we are getting more than 10 units of monosaccharides, and they are generally not sweet in taste, and these are also called as non-sugars. For example, starch, cellulose, glycogen. Glycogen is like the animal starch. Okay. So starch is made up of some n number of units of alpha glucose. Okay, what is alpha and beta glucose? I'll explain you in some time. So most of the plant food will have the energy stored in the form of starch. Okay. So they are all made up of glucose. Cellulose is also made up of glucose, but that is about beta glucose. And most of the plant cell walls, right? Skins, cell walls, these are all made up of cellulose. Next is glycogen. Glycogen will also have n units of alpha glucose. Mostly this is an animal starch which is stored in liver and animal food. Okay. So these are three main classifications based on the number of uh, based on the hydrolysis of the sugars. Okay. Second classification is based on functional groups. That is, sugars could be either aldehyde based or they are keto based. If they are aldehyde based, we call it as ald and O's. O's means sugar. Okay. So ald O's, which are aldehyde based sugars, ketos, which are ketone based sugars. Got it? For example, smallest of the aldehyde, which is a sugar, basically it has to fit in the definition of sugar, is you can see polyhydroxy aldehyde, correct? So the minimum polyhydroxy aldehydes to fit, we require at least three carbons. Second and third carbon has to have OH group, and one carbon has to have aldehyde. Now, this minimum or the basic sugar or the first sugar, smallest sugar, that is called as glyceraldehyde. Okay. And since it is coming from an aldehyde, we call it as aldose plus three of them. There are three carbons, right? One, two, three carbons. It is made up of three carbons. So that is why it is called aldo tri and O's. So this is aldotriose. Similarly, if you have a keto form, then it is carbon 1, 2, and 3. And on the second position, you can see keto. And here we have hydroxy and hydroxy. So polyhydroxy. So therefore, this is also keto triose. This is also sugar. But have you noticed this is one of those exceptions where there is no chiral molecule. So there is no chirality here, but yet that is a sugar. Okay. So this is called as keto triose. Now imagine if I increase one more carbon, I get one extra OH here and OH here and CH2OH here. So can I call this what? I mean, what do we call it? This is called as aldotetrose. Okay. Similarly, this will become ketotetrose. Okay. Now, glucose, because it has an aldehyde on it, so we call it as aldohexose because there are 6 carbons, while fructose is ketohexose sugar. Okay. So this is the third classification, wherein we are checking out number of carbons and deciding what type of sugar it is and which family of sugar it belongs to, whether it belongs to aldehyde or ketokine. Next, before going further ahead into the uh, various forms of sugars, first let us dig a bit into DL configuration. What is this capital D and capital L stands for? See, the capital D, capital L is in reference to the first of a kind of aldehydes and ketones. Now, let me just focus mostly on the aldehyde part of it. When it comes to aldehydes, the first of the sugar we can expect is a glyceraldehyde, correct? So, because this is the minimum number of carbons required to, represent itself as sugar, and it will have a chiral center here. On this chiral center, if at all I put the CIP rules here, you know that this is priority wise 1, priority 2, priority 3, and priority 4. And notice something carefully that 1, 2, 3 is moving across anti-clockwise direction, which means it is a R configuration, which means it is an R configuration. Likewise, if you notice here, we have OH, which is priority 1, priority 2, and priority 3. If it moves in a clockwise direction like this, then it is going to be S configuration. It is going to be S configuration. So one is R configuration, the other one is S configuration. Correct? Now, what has been noticed is that if I take glyceraldehyde, correct, and we observe its angle on the polarimeter, it is found to be dextrorotatory. This is found to be dextrorotatory. And you know that general representation of dextrorotatory experimental rotation, what we are seeing, we always represented by small d. So this one is found to be, because it's a mirror image, it will be minus, and that will be small l. Okay. So if you keep increasing one carbon above, that means from glyceraldehyde, if you start increasing one carbon more, like this here. So I have, this is a glyceraldehyde, and I add one more extra carbon to it, make one OH and H, OH and H, like this. Now what I'm doing, I'm not changing this part of the chain. This part of the chain is intact. In this part of the chain, the OH is always on the right hand side, just like the dextro form of the glyceraldehyde here. You can see it is on the right hand side. Okay. That is the reason why we call this as a D family, capital D family. So now we are trying to draw a capital D family tree. Okay. It is more or less like an ancestral information. For example, if at all I want to figure out, about my family details, correct? So I would see what was the name of, what was my surname, where did it come from, who are my, ancestors, who are my great grandfathers, everybody from that lineage I would like to check, correct? So if you notice something for all our bloodline, something would be common. The common is the surname most of the time, or a place. Some people get the surname as a place of the birth or based upon their profession. Something like that, you'll get a surname followed, correct? Likewise, if you start drawing a family tree for glyceraldehyde, okay, From here, imagine that glyceraldehyde has two sons or two daughters, or son and a daughter, anything. That means two children. So okay, one child have, you know, OH, OH on the right hand side. One children has OH on the left hand side. Okay, because they both belong to the same bloodline. This part is not changing. You can see this part will remain intact, and that part is what we call it as capital D. So that symbolizes that capital D means that last carbon's OH is always on the right hand side in the Fisher projection. Okay. So capital D is more or less like a tagging of their family information. So D family, after adding one extra carbon, if I put the OH on the right, it will become D erythros. If I put OH on the left, it will become D threos. This is the name given. Just like glyceraldehyde is a name here. So this is a capital D glyceraldehyde. Okay. Glyceraldehyde. Now this would become capital D erythros. This is capital D threos. And again from erythros, if I add one more carbon extra, so there again I can write OH on the right or OH on the left. When you write that all OH, if they are appearing on the right hand side with three chiral centers, that is called D-ribose. The name given is D-ribose. Now here one of them is on the left hand side, that is D-arabinose. While threose, when you add one OH on the right, that will become D-lexose. Okay, sorry, xylose. And if the OH is on the left, it is called lexose, xylose and lexose. So four different new, I mean, for erythros, imagine like he got two children, and threos, this person got two children. So here it is ribose and arabinose. Here it is xylose and lexose. And then when you have ribose might again have two children. So that is D-allose and D-altrose. If all OH on the right hand side, it is allose. Okay, remember it right? All. All means all of them. All of them on the right hand side. So all of them on the right hand side, it is allose. One of them on the left hand side, altrose. Okay, and then this one is on the right hand side, that becomes glucose. So you can see the D-glucose is derived from this family of glyceraldehyde, from erythrose to arabinose, finally to glucose. This is the family tree of glucose. Okay, likewise for arabinose, if I put the OH on the left hand side, that would become D-mannose. Okay, similarly, if at all I have xylose, for xylose, if at all I put everything this on the right hand side, it is gulose, left hand side it is idose. For lixose, if I put right hand side, it will be galactose, left hand side it will be thallose. Now, sir, do we have to remember all of them? Honestly, no. Mainly, you have to remember this. Okay, so I'll just mark it down for you to remember here. You have to remember what is erythrose, what is ribose, what is glucose and mannose. Here you need to remember what is ribose. That's it. Okay, at least this many parts you have to remember. Correct? So, right from glyceraldehyde, obviously, then erythrose, ribose, arabinose, glucose, and mannose. So this is a family tree of D sugar, capital D sugar of aldehyde kinds. Everybody clear? If you have a doubt, you can ask me now. Okay. So we could remember it in many different ways. Okay. So it is up to you how you want to remember it. Okay. This is one way I would remember it. Get, G-E-T, get. Then we have rag, R-A-G, rag, or rag. Okay. You can remember it either ways. Get rag. Okay. Clear? Or, I usually remember it in Telugu as get ragam. Got it? So G-E-T, get R-A-G-M. So that makes it easy for me to remember. It starts with galactose, erythrose, threose, ribose, arabinose, glucose, mannose. Okay. Let's understand this definition. What is epimers? Okay. Now, We know that if two molecules are stereoisomers, but if they are not mirror images of each other, we call them as diastereomers. Okay. So if I take these two sugars, I compare them, and if they are stereoisomers, that means they are stereoisomers but not mirror images, then I know they are diastereomers. And if particularly in those diastereomers, if they have an opposite configuration only at one chiral center, rest all the chiral centers are same configuration. Only the variation is at one chiral center. Then we call those diastereomers as epimers. We call them as epimers. Okay. Let me show you how. For example, if you take glucose and mannose. Okay. Glucose, check out OH, 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 OH. Everything is same so far. Only one change. This is on the right hand side. In mannose, it is on the left hand side. So I can say that only at this location, the configuration got changed. Rest all, everything is same. So if the configuration is changed only at one location, then we call those two molecules as epimeric pairs or epimers. And since glucose is showing an epimerization with mannose and the second carbon, so we call mannose as a C2 epimer of glucose. Similarly, if you compare glucose with galactose, you will see at fourth position there is a difference. Rest all, rest all structure is exactly same. So we call this as a D-galactose, which is the C4 epimer of glucose. Similarly, C3 epimer of glucose is allose. C5 epimer of glucose is idose. Okay. So these are few epimeric forms which we need to know. Glucose has multiple names. Okay. Industry wise, where exactly it is used, we'll name it differently. Dextrose is one such name. Dextrin in pharmaceutical industry it is most used, right? In food and beverages, it is used as grape sugar. These are the names that are being used. The preparation wise, glucose is very simple. You can use starch or sucrose, hydrolyze it. You will get glucose and fructose. And glucose and fructose can be separated by different means. And if at all we have starch and directly react with dilute H2SO4 and boil, you get only glucose here. So this way you can prepare glucose very easily. Okay. Now, what are the typical reactions of glucose? Check out. These reactions will also help us confirmation of the structure of glucose. So we'll start with the first one. Check out first case. If we react with HCN, since there is an aldehyde group, HCN will react and make a cyanohydrate. So we will get a product like this, CH, we will get this as OH and CN, and then we will have this as CH, OH 4 times and CH2OH. This is the product which you will get. So this is cyanohydrin. Okay, glucocyanohydrin. 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 Glucocyanohydrin has a lot of advantages. That is, in case if you hydrolyze this here, cyanide will get hydrolyzed here. So we'll get CHOH, COOH, and then we'll have CHOH 4 times, and then we'll have CH2OH here. Correct? Okay, so OH and COOH is what you will get here. So this is like alpha hydroxy acid. So it is like alpha hydroxy acid. Okay. This is the reaction with HCl. Next. Next is NH2OH, hydroxyl amine. NH2OH is called as hydroxyl amine. If we treat with a hydroxyl amine, it is a mild acidic condition need to be taken. And in that case, we will get this as CH double bond N NOH, and then we will get this as CHOH 4 times. This is CH2OH. Okay. So now this is an oxime form. So that's why it is called glucoxime. glucooxime formation. Okay. Usually oximes are colored. Usually oximes are colored. Okay. And more importantly, whenever you react with this one, if you are getting a colored molecule, this is a confirmation that there is a presence of aldehyde or ketone. So this is presence of, sorry, confirms the presence of aldehyde or ketone. It could be anything with aldehyde or ketone. Both, in both cases you will get oxime, and both of them will be colored. Okay. See the third reaction. If glucose is reacted with bromine water, bromine water is a mild oxidizing agent. It would slowly oxidize aldehyde into acids. And bromine water, which is a brown, reddish color solution, it will slowly start fading out. So you will get this as COOH and CHOH four times and CH2OH. Okay. So you can see bromine is a mild oxidizing agent. So it is slowly oxidizing the uh, aldehyde into acids. Uh, Alcohol, 1 degree alcohols can also get oxidized, but it is a very, very slow process. So usually we can immediately say that after this, since the bromine is almost losing out its color, so we can confirm the presence of aldehyde here. Okay, confirm the presence of aldehyde because it is coming from a glucose, right? So we call it as a gluconic acid. Gluconic acid. Okay. In fact, generally, if you are getting any aldehyde or aldoses to convert into an acid, we call it as, aldonic acid. So this is aldonic acid. So onic, remember this, onic. Onic is the word that we use, onic, which means single oxygen, single COOH group present, which is coming from sugars. And this will make a confirmation. So that is confirms the presence of aldehyde, confirms the presence of aldehyde. So why I'm saying that, if it was a ketone, this bromine would not have responded at all. So there will not be any decolorization. So this confirms that glucose is actually an aldehyde. It is not a ketone, but an aldehyde form. Okay. So remember, the first two reactions is to deal that there is an aldehyde or a ketone. Third reaction is to deal that there is an existence of aldehyde. Next is acylation. Acylation is when you react the glucose with AC2O, which means an anhydride in the presence of pyridine. So imagine if there was any alcohol present, they should convert into esters, undergo esterification. Okay, it should undergo esterification. Clear? So now what do we get here? So this CHO will not be disturbed here. That CHO will remain the same. But next we will get this as CHOAC four times, and we will get this as CH2OAC. So total, it shows the existence of 5 hydroxy groups. Okay, it shows the existence of 5 hydroxy groups. This can be determined both practically, I mean quantitatively and qualitatively also. Okay, so here there is a glucose with a penta-acetate form. So this is called as gluco glucopenta glucopenta-acetate glucopenta-acetate form. Okay. Now, this actually suggests that there is an existence of 5 OH groups in glucose, isn't it? So this is confirming the existence of 5 OH groups. Clear? Right. And notice this one. Generally, every time, suppose if the molecular weight for this one, molecular weight is 1 here and molecular weight is 2 here, then number of OH groups present, okay, OH groups present quantitatively, how do we figure out? We will take out the difference in the molecular weight and for each acetate, the weight increased is 42. Molar mass is 42 when you remove hydrogen and put it with acetate. So in the case of glucose, if you calculate that, this minus this divided by 42 will come out to be 5. Okay. In case of glucose, the number of OH groups will come out to be 5. Okay. So this is about acylation. And second important thing is that once you have a penta-acetate form, and now when you try to react with NH2OH, it becomes very difficult to react. So this one will not give any reaction. No reaction. Okay. This suggests that CHO form is not present anymore. Not present anymore. Now, why is that not present? We will go ahead and learn it. But this is the idea that you will get. Okay. So first you'll get that there are 5 OH groups by making acetylation. And then after that, when you react with NH2OH, which is also suggesting there is something happening to this aldehyde. So because now it is not giving any color formation. Next, dilute HNO3. When you treat with dilute HNO3, the aldehydes will convert into an acid. So here this will become an acid by oxidation. The secondary alcohols does not get disturbed with dilute HNO3, but the primary alcohols will also get oxidized to acid. This is the acid which you will get. Now, since it is glucose, derived from glucose, it is gluc and aric acid. Aric means on both ends, okay? So just like earlier, it is onic acid means only one end. Now it is aric acid. Aric acid means both ends. So the alternative name, if you come across aldehydes and do this similar acid part, we call it as aldaric acid. That was aldonic. This is aldaric. Or another common name used is saccharic acid. It is also called as saccharic acid. Got it? This is the saccharic acid form. So, well, HNO3 is not giving any conformation as such, but it is an important reaction. Okay. This is giving glucaric acid, aldaric acid, or saccharic acid. Next, reaction with HI, red phosphorus. If you treat with red phosphorus, you know that everything will get reduced and convert into only alkane form. 1, 2, 3, 4, 5, 6. So what we are getting is N-hexane. Now this gives a very important confirmation that glucose, in glucose, there are no alkyl branching. So there is no alkyl branching observed. It's a straight chain because you are getting N-hexane. So N-hexane suggests that it is actually a straight chain carbon. Yeah. So have you noticed that this sixth reaction, fourth reaction, third reaction, second reaction, these are mainly the reactions that are used for confirming the structure of glucose. So they clearly suggest how the glucose looks like. Okay. Next, oxidation with Tollens or Fehling's and Benedict solution. See, if you react with Tollens reaction, so Tollens means if you have silver ammonium complex, then this CHO will convert into COO minus because we learned this in aldehyde already. So this will remain 4 and CH2OH. And here silver will get uh, reduced. Silver will get reduced here. Okay. Which we usually call it as silver mirror test. And the same thing would happen here also, which we call it as failing solution. So failing solution is also same with precipitate as CO2O, which is brick red precipitate. Brick red precipitate. Okay. And remember, glucose is a reducing sugar. Okay. Glucose is a reducing sugar. Reducing sugar means it will get easily oxidize itself to convert into acid form, and silver or copper will get reduced form. Clear with this nature of reaction, oxidation reaction? Hmm. Next, eighth one. What if I keep glucose in dilute OH minus? Suppose if I add a dilute OH minus into glucose solution, what will happen? See, first of all, this is the structure of glucose. Okay, the Fischer projection of glucose. And then when you keep the OH minus in it, you will notice something that this CHO, I mean, it will undergo tautomerism with respect to this hydrogen. And during the tautomeric step, when this hydrogen goes here, double bond will shift here. And now when the double bond is here, again when it comes back to aldehyde, you can get an OH here also and double bond O here also. Okay. So let me show you that. For example, here, imagine if you have a fructose form. You can take fructose also, glucose also, anything. Let's say fructose form. For this ketone, how do we write the enol? I will take this hydrogen, put it here and convert this into double bond. And that's what I have done. Now, have you noticed something? The above carbon structure and below carbon structure are same in terms of connections. This also has OH, this also has OH. Which means this hydrogen can come here, make a double bond here, or this hydrogen can come here and make a double bond here. So chances are it can get both type of aldehydes. It can get a glucose aldehyde, it can get a fructose aldehyde, or it can even go back to the mannose, and here it can go back to the fructose form. So glucose, mannose, and fructose, all three can be interconverted. Okay, clear? All three can be interconverted. So for example, if I take glucose here, it can convert into fructose. It will maintain an equilibrium with fructose. And that can be converted into mannose. So we will always see to it that these three will exhibit an equilibrium mixture when you add it to dilute OH minus. Okay. Clear? Now, there is a name given to it. Okay. So this is Lobre de Lobre de Brian, Lobre de Brian Van Eckenstein, Eckenstein transformation or rearrangement. This is the name. Okay. LBVE. LBVE. Lobre de Brian Van Eckenstein rearrangement. Okay. That is basically interconversion of glucose to fructose, fructose to mannose in basic medium. And after a while, you will notice that once they reach equilibrium, almost you will see 33% of this, 33% of this, and 33% of mannose present at the end. Okay, please check it out. The right. Next, check out reaction with NaBH4. NaBH4 is a reducing agent. It will reduce the aldehydes into alcohols, right? So which means you will have this as CH2OH connected with CHOH four times and again connected with CH2OH. Okay. So since it is derived from glucose, it is called as glucitol, glucitol, or industrial name is sorbitol. It is also called as sorbitol. Done. Next. Next, what happens if you have glucose reacted with, concentrated H2SO4? On reacting with concentrated H2SO4, right, conc H plus, it will get charred. Charred means it will start becoming crumbling into a powdered form. That is called charring of glucose, and that will be appeared as carbon black, and huge amount of energy is released. So that released energy will be coming in the form of steam. Okay. So concentrated H2SO4, if you have even added to this cane sugar or sugar common, the sugar which we eat, that will also get charred into carbon and H2O vapors will be released. Okay. Next is the 11th reaction. This is an important reaction again. This is a reaction with phenylhydrazine. Phenylhydrazine. For that, we require 3 moles of PHNH NH2, which is phenylhydrazine. The product name is called glucose-osazone. If it is coming from glucose-osazone, we call it as glucosazone. It is usually yellow colored crystal form. It is a yellow colored crystal form. And along with glucose, it will give the same reaction with C2 epimers from osazone, which means if you take the C2 epimers of glucose, which is mannose, so glucose and mannose will give the same reaction. And glucose, mannose, fructose are interconvertible. So even the fructose will also give the same reaction. So remember, glucose, mannose, fructose, all three will give you same type of osazone. Okay. Likewise, D-glucose, D-fructose, D-mannose, same osazone. D-glucose, D-iodose, same osazone. Galactose, thallose, same isozone. Okay, same osazone. Got it? Let me show you the product first and then I'll show the reaction, how it works. For example, if at all I have glucose, this is, let's say, glucose. It could be D-glucose or an L-glucose. And now what would happen here is this part would convert into CH double bond NH and NH and pH like this. Second carbon will also convert into the same form like this pH. And then we have CHOH three times, correct? And then we have CH2OH. This is the final product. This is osazole. Okay. Now let me show you the mechanism here. How does it work out? So basically, first we know that when you have C double bond O and CHOH four times and CH2OH, if you have this here, first reaction that is pH, NH, NH2. As these two react with each other, first we'll get C double bond N, NH, pH. This is the first thing we'll get. Okay. So we know that aldehydes and ketones reaction with ammonia derivative. So this is that ammonia derivative reaction. So then we will have this as CHOH four times and CH2OH. This is the first thing that is formed. Now, if I take the same structure, what's happening here? Check it out. So we have something like, this carbon is basically having, second carbon is having CH here, CH, and then we have uh, OH, CH and OH here. Okay. Since it is CH and OH, this nitrogen will try to take the H plus from here, and that will push this bond to become double bond, correct? And as they start becoming double bond here, this nitrogen, I mean this double bond will get tautomerized here. Okay, sorry, that double bond O will be present here, and this side we have a group on this position. Okay, clear? So in that case, we will get C double bond O form here. One second. One mistake I made. NH. Oh, sorry. First, let me tautomerize. Okay. Second step, I have to write that. Sorry. First, let me show the tautomeric form here. For example, if I take H plus from here, you'll get a double bond here. This nitrogen will take the lone pair. This is like the tautomeric form. So I will get this as H, C, double bond C with N and H connected with N, you know, NH and PH. This is how it is present. And then we have O and H here, correct? O and H. Clear? So now this time the lone pair from here will try to take H plus, and that will convert into a double bond, and here this will convert into a double bond on this position. So it would convert into HC double bond NH with, NH, because you could notice that this is becoming NH2 plus. So to remove, to make the bond proper, you have to break this bond onto this side. So there will not be any bond afterwards here. Then we will have C double bond O, and below it is continued. This means, this ribbon means this is continued below. Okay. So plus PHNH2. So this is a product formation. Okay. So this is a product formation. Okay. So first we will get this CHNH. And now notice this one. Now when you react with 2 moles of and then because the water is present in the solution, imines are highly unstable. So first imines will convert into an keto form once again, and ammonia is released. So it is like a ketoaldehyde form. This is the intermediate that you need to remember. Now from this intermediate, this time when you react with 2 moles of PH NH NH2, now we will get this as HC double bond N and NHPH. Second also C double bond N NHPH, and below we will have like this. This is the product form. So this molecule, what you are getting, the first two carbons. So what is the learning from here, guys? Is that it is all about the first two carbons. If you have the next four carbon structure same, so all of them will give the same structure. I mean, say all of them will give the same oxazone. That is why if you notice glucose, fructose, mannose, their structure from third carbon to the sixth carbon is exactly same. The only difference is in the first two carbons. Therefore, they both will give you the same oxazone form. Clear? Please check it out quickly. What is oxazone? How does it happen? Next, let's see the next reaction of glucose. The next reaction is with periodic acid. Periodic acid, we have done it many times, okay, in alcohols also. So let me quickly remind you. The reaction goes like this, where you need to find out the vicinal diols, that means OH and OH adjacent to each other. If they are adjacent, we just have to break the bond. Let me show you how we can break the bond here. Check this out. So first we will break it here. So whenever you are breaking the bond, correct, you have to introduce one OH above and one OH below, like this, and like this. So we'll introduce one OH above and below. You can see one OH down, one OH up. Here also one OH down, one OH up, one OH down, one OH up. Here also one OH down, one OH up. Here also one OH down and one OH up. Okay. So check it out. In this case, the carbon has two CH and two OH groups. Two OH groups would convert into aldehyde, while this carbon here has one hydrogen and three OH groups. Okay, and three OH groups will convert into acid HCOOH. So you can see these three will also do the same thing here. They all will be doing the same job. So all of them will have three each. So they all will convert into acid. And the last one here, it is same as the first one, that will convert into an aldehyde. So this is what you will report as the final product. And how many cuts you make? 1, 2, 3, 4, 5. So that means I require 5 moles of HiO4. So with 5 moles of HiO4, we shall get this as 5 moles of HCOOH, correct? Okay. So 1, 2, 3, 4. Sorry, 4 moles. No, 5 moles, 5 moles, right? Why, I forgot this. Here, this is double bond, not CO. So here we have no hydrogen here. Sorry. It is actually a double bond O, and then I got one OH. So that is actually an acid part. So it is HCOOH. Okay. So 5 moles of acid and 1 mole of aldehyde. So this is after the oxidation of glucose. Clear? So with periodic acid, glucose will convert into 5 moles of formic acid and 1 mole of formaldehyde. Okay. These are all the important reactions of glucose, whatever we have learned so far. Now let's dig into the structure of glucose. How does the structure of glucose look like? Okay. See, glucose apparently has two type of structures. One is an open chain structure. The other one is a cyclic structure. First, let's understand what is open chain structure. Open chain is the one which we write it as a Fisher projection. This is the Fisher projection when you have an open chain. In open chain, aldehyde is available. Aldehyde form is available. Now, cyclic structure is the case where glucose typically does not show any carbonyl reactions. That means it does not show any reaction with Schiff reagent. It does not show any reaction with sodium bisulfate. It does not show any reaction with 2,4-DNP. In fact, all three were, very good reaction basis to identify aldehydes, correct? Aldehydes are, in fact, carbonyl groups. So, and all three were rejected. So that means the glucose can exist in two different forms. When only it is in open chain, we might see these reactions happening. But if it is in a cyclic chain, you will see all these reactions will be negatively observed. Now, second evidence for glucose that it is showing, glucose that it is showing a cyclic structure is if I take glucose in general and add one more of methanol in dry HCl, okay, we are expecting an hemiacetal to form, correct? Because it is an aldehyde. When you add one mole of alcohol, we should get hemiacetal. But we are expecting only one hemiacetal, but unfortunately, you will see there are two hemiacetals forming, and both of them are having different melting point. which clearly suggests that there must be some kind of a chiral centers, but they will be diastereomers of each other. So there is an alpha methyl glucoside, there is a beta methyl glucoside. Both of them have different melting points. So this also speaks like an evidence that there must be some kind of a cyclic structure present here. Okay. So glucose is in general not an open chain form. Instead, it exists in a cyclic hemiacetal form. Okay. The third evidence that it is present as a cyclic form is when you make a pentaacetate of glucose. Once it becomes a pentaacetate, now if you try to react with NH2OH, you would hardly find the presence of aldehyde anymore. So this also indicate the absence of the aldehyde group present on glucose. Okay. So check it out. Suppose if this is the original structure of glucose, this is how it is present. And you know that this is RSR configuration and this is also R configuration at the end. Okay. Now, to just keep this configuration R only, I can put this OH on the, at this position also. But for that, we learned in Fisher projection, we have to make even number of exchanges. That means I'll put CH2OH here, this OH here, that is exchange number one. And then CH2OH on the left, H on the right, that is exchange number two. So you can see after exchange two exchanges, you will get this form. So this configuration will still remain R only. So we are not disturbing that molecule. Now, if at all I put this in a slant form, do you remember that Fisher projection is all about these groups coming out of the plane like this? These are all coming out of the plane while this is going inside the plane. These two are going inside the plane. Correct? So imagine if at all I take this molecule and write it in a slanted form just to show that this molecule is inside, this was also inside. Okay. So now if at all I have this CH2OH, I start curving it. Imagine it will be like a vertebrae, a spine. I took this as the spine here and make some curve. In that position, now originally OH was here. To bring this OH here, I need to make even number of exchanges. So this is even number of exchanges. So you can see, I can make this even number of exchange here. After even number of exchanges here, now you would actually notice that this OH has a much closer distance to the C double bond O. So internally, we can have an hemiacetal form. That is, this lone pair can attack, this will become O minus, and this O minus can take H plus. That way, you can get a hemiacetal form and the ring will get closed. Okay. Now, if the ring close is observed here, you notice something important, that here it appears as if this part of the molecule is coming out of the plane. This part of the molecule is coming out of the plane here like this. This way it is coming out of the plane. Okay. And this part is inside the plane. And these are up and down on the plane. These are all up and down on the plane. Okay. This representation, a cycle which is going inside and out, right? For us, it is like inside and out. Rest of the groups are up and down. If I put that way, these cyclic structures are called as Haworth projections. These are Haworth projections. So you could notice that we can get an Haworth projection of glucose here. Now, another thing, when this OH is attacking from this end, I can say either this evolved new OH will be on the upside or new OH will be on the downside. Correct? So that means OH could be down here, on that Haworth projection, or OH could be up on the Haworth projection. It makes sense, right? Because it is an sp2 carbon. It is planar. So the attack of O can be happening from the top or from the bottom. So you get two structures. Now listen carefully. If this CH2OH, which is on the top side in the Haworth projection, and this OH, which is on the bottom side of the Haworth projection, if these two are opposite, one is up and one is down, then we always read that as an alpha isomer. If the CH2OH and the OH both are on the upside or both are on the downside, then we read it as beta isomer. And since it is coming from glucose, we call it as alpha glucoisomer. And this is beta glucoisomer. This is alpha glucose or beta glucose form. Okay. And these are two Haworth projections. Clear, everybody? And it is like the configuration wise, everything is same. See, structure is everything same. Or except one difference, that is the configuration here. Absolute configuration here is different, because in this case oxygen is down, in this case oxygen is up. So can I say, if a configuration difference happens only at one carbon position, generally we call it as epimers. But here, if that carbon is a hemiacetal carbon, it has a different name, and that name is called anomer. That is called anomer. Correct? So an epimer, which is observed only changing at one position, the configuration changing is only one position, that too at a hemiacetal position, then we call it as anomers. Okay. So alpha glucopyranose, beta glucopyranose, these two are the names of these two, and these two are anomers of each other. These two are anomers of each other. Now, what is this pyranose means? See, basically, if you notice, the structure of glucose is replicating a six-membered ring like this. This six-membered ring's common name is pyrene. This is pyrene. So that is the reason why we call it as pyranose. This is forming a pyrene structure and it's a sugar. So that's why it is pyranose. So it is glucose making a pyranose, glucopyranose. Okay, sorry. Check. So alpha glucopyranose, beta glucopyranose. These two are anomers of each other. Okay. Why pyranose? Pyrene is derived from the structure pyrene. Clear? Please look into it, everybody. Check how the structure is made into, cyclic structure is made into Haworth projection. You can please talk to me if you have any doubts, I can discuss. Now let's see the next concept. What is mutarotation? Okay. See, when it comes to glucose, its straight chain form is hardly observed. Most of the glucose, when it is in a powdered form, it gets either crystallized into alpha glucose form or it gets crystallized into beta glucose form. Okay. Straight chain composition is hardly 1%. The high percentage would be for beta glucose and slightly less percentage would be for alpha glucose and the least would be for straight chain. Okay. And if you see apparently how much amount of angle of rotation that it creates, correct, is approximately, this is around 113 degrees. When you isolate this and uh, measure the angle on the polarimeter, it will be 113. Here this will be around 19.5. Okay. And straight chain, we know that it is 57.2. Correct. This is the angle which you will find. So theta now is, because in a when you take sugar, you will not get actually complete alpha glucose or complete beta or complete straight chain. You might always have a mixture. So if there is a mixture, you will not find an exact angle of 1, 2, 3, any one of these. Rather, you will get the average of this. 36 into alpha, the angle is 113 plus 1 degree into 57.2 degrees plus 63 into 19.5 degrees. This whole divided by 100. That would be equal to 52.5 degrees Celsius. 52.5 degrees. So this 52.5 degree is called as mutarotation, which means we are not exactly getting the rotation of one particular kind, we are getting the rotation of a mixture kind of a weighted average. Okay, so check. So the change in specific rotation till the equilibrium mixture is formed, that is called mutarotation. Okay, I hope the idea is clear what is mutarotation means. And now notice this one. When it comes to stability wise, okay, beta glucose, beta glucose is more stable than alpha glucose. Beta glucose is more stable than alpha glucose. Now, why is that happening? Have you noticed that these are six-membered ring? Since it is a six-membered ring, it must, since it is a six-membered ring, it must be in a chair form, correct? You notice this is the chair form which you'll have, and oxygen would be at this position. Okay. Now, let me bring this beta glucose here for, for the sake of understanding here. How does it look like? So let me show you this reference. So trying to uh, I'm trying to draw the chair form for beta glucose. Okay, this is beta glucose. So what would we do? We'll try to keep the this kind of group CH2OH, which is slightly bulkier group, always on the equatorial position. So let me place that. So this is how we'll place it at equatorial position. So this is like CH2OH, and the adjacent group is trans to it. These two are trans to it. Trans means equatorial, equatorial is trans. Here also we have OH. And the next group, this OH and this OH is also trans to each other. So, which means this OH is also equatorial. And next, this OH and this OH is also trans to each other, which makes this OH also equatorial. And this OH and this OH is also trans to each other, which makes this OH also trans. So this is the beta glucose form. Okay. Now, when it comes to alpha glucose form, you know that structure wise everything is same only, alpha and beta. Only changes the OH group, last OH group. So if you notice this last OH group will be on this direction here. So this is axially aligned. While when you have beta glucose, this is equatorially aligned. And you know that when it comes to an axial and equatorial forms, which one is more stable form? Always equatorial form is more stable. So that's the reason why if you compare the stability of these two, so you would typically find that beta is more stable than alpha. And since it is more stable, definitely we can expect the quantity of that molecule will also be more. So quantity of this case will also be more here. Okay. I hope you guys understood. This is called the chair form of it. Now, just as a note, I can write it down that when it comes to mutarotation, okay, when it comes to mutarotation, we can say that if you have uh, any, sorry, any sugar, any sugar which exist in hemiacetal form, hemiacetal form, right? It is, it will naturally show a reducing sugar nature. That means it can reduce the Tollens Fehling's Benedict solution. At the same time, it will show Mutarotation. So mutarotation. So if a sugar has to show any of these two properties, reducing sugar property or mutarotation property, what is the one thing that we will check? Whether it exists in a hemiacetal form in its cyclic structure or not. So if it exhibit hemiacetal form, that means they will show these two properties. Everybody clear? Done. Now let's talk about fructose. The Fisher projection of fructose is like this: 1 to 6, and configurations are SRR configuration at 3 chiral centers. Okay. And now, just like glucose, fructose also shows its cyclic nature. And this time, the skeleton which it adapts, of course, it can adapt 6-membered ring also, and it can adapt 5-membered ring also. So, depending upon temperature conditions and the orientation of the molecule, it is been noticed that the fifth position's OH attacking on the second position keto form. This is most likely observed. So from the fifth position, this O get connection on the second carbon. And on the second carbon, you have CH2H as one group. Now this will convert into OH group. So this is OH group. Now mind you, these corners are not carbons. Okay, this is just to show the connections. So remember, these are not the corners of carbon. It is just a connection to show. So while this fifth position onwards, when the connection establishes, you can see the OH could be on the right hand side or the OH could be on the left hand side. Okay. So if the OH is on the right hand side in the Fisher projection, typically we call it as alpha fructose. And the 5-membered ring, 1, 2, 3, 4, 5. So it is forming a 5-membered ring. A 5-membered ring is a derivative of furan structure. This is furan. That's why the cyclic structures are termed as fructofuranose. So it is alpha fructofuranose. If on the Fisher projection OH is on the left hand side, it is beta fructofuranose. Fructofuranose. So these two are the existence of these two are the alpha and beta existence of fructose. Check it out. In this case here, if you notice, we have carbon 1, 2, 3, 4, 5, and 6. These are the 6 carbons we have. So what do we call it? Now, the same logic earlier, what we kept, I'll do the same thing here. This OH is pointing down, while on the 6th position, CH2OH is pointing up. So when they are opposite, we call it as alpha. So alpha fructo, alpha fructofuranose. And same way, if you notice, CH2OH on the 6th position, OH on the 1st position. If these two are on the same side, it is beta fructofuranose. So this is beta fructofuranose. So fructose exhibits in these two structures. Alright. Now check the cyclic projections of glucose, fructose, and other sugars. These are called as the Haworth projections. Okay. Just like in glucose, fructose also have beta anomer more stable than alpha anomer. You don't need to learn the reason out of it, how the structure is and all. In this case, you just remember it that beta is greater than alpha anomer. Okay. And check one thing carefully. This is a carbon, second carbon. It has some R group, OH, and O group, correct? So it is like this is OR and OH. So that means this is hemiacetal only. On second position here also it is hemiacetal only. So both of these are hemiacetal forms, and when there is hemiacetal form, what are the properties we check it out? That it will act like reducing sugar, as well as it shows mutarotation. Shows mutarotation. Here, now let's quickly talk about disaccharides. Disaccharides. There are mainly three disaccharides you need to learn. The first one is sucrose. First one is sucrose. Sucrose is when you have the first carbon of alpha D glucose bonding with the second carbon of beta D fructose in its cyclic structure. When the connection establishes, they will become from hemiacetal, they start becoming like an acetal. Okay. You know that if a carbon has one OH group and one OR group, we call it as hemiacetal. And while if it it has been reacted again with alcohols and it appears like OR and OR, then we call it as acetal. Correct? When we call it as acetal. Now that is the same thing happening here also. We learned that this is the alpha glucose or alpha glucopyranose. Okay, one second. Right. So this is about alpha glucopyranose and this is beta D fructofuranose. Okay. Now our objective is to make a connection between carbon 1 of glucose and carbon 2 of fructose. But since they are on opposite directions, it becomes difficult to make any contact. So what I am doing, I am taking this axis on this axis, correct? Okay, this axis means how, first let me show the structure so that clear about it. See, I told you that this part of the body is coming out of the plane in the Haworth projection. This entire thing is coming out of the plane. So basically, I am drawing a plane, an axis here like this way. This is the axis I'm talking about. Okay. So if across this axis I rotate it by 180 degrees. Okay. So that means I have it like this and I'm tilting it completely this way. So it is like this, just like my palm, you can see, okay, how my hand is twisting like this. So which means now notice this one. Suppose on my hand here, the way Haworth, this is my Haworth projection form. So on the Haworth projection, some groups are pointing up, some groups are pointing down. So suddenly, if at all I tilt it around, so you can see the groups which are up are going down and the up are going and the down are coming up. And that's what you have to do it now. So in fructofuranose here, so when we write this into this five-member ring here, so oxygen like this way. And now you can see the second carbon which was here, now it will come at this position. So now this will become second carbon, fifth carbon, this will become third carbon, and this will become fourth carbon. Okay. And now on the second carbon, what will happen? CH2OH, which was coming down earlier, now it will go up, and this OH will be down. Similarly, on the fifth position, H will go up and CH2OH will be down. Okay, clear? So I suppose this point is clear, right? Next, on the second position here, because this OH is coming down, so the position will remain almost the same. That is, OH will be down here, H will be up here, and here also we will have H will be down, OH will be, OH will be up and H will be down. Okay, so this is the rotated structure of beta fructofuranose. Now, how does that make an advantage? Now, you see, that is the same structure I have drawn here, correct? Now, how does it make it importance for us is that now carbon 1 here, carbon 1 which has an OH and carbon 2 of fructose which has an OH, this part we have to dehydrate. We have to remove this as water and make a connection between them. And again, let me tell you, these are not, okay, coming, coming. So these two are not the carbons exactly. So we will have this carbon making O and some R group, and this carbon is making some O and OR group. So from both ends, from carbon 2 also and carbon 1 also, this has become an acetal form. Now this connection, the yellow form which I have written here, this connection is what we call it as the glycosidic linkage. This is called as glycosidic linkage. Okay. So the so-called structure what I made right now, where we have alpha beta glycosidic linkage, alpha and beta together we are making a glycosidic linkage that forms sucrose. Okay, so that forms sucrose. Clear, everybody? Done. Now, what are the properties of sucrose we need to know? So sucrose is completely non-reducing sugar. Why I'm using the non-reducing sugar now? Because there is no hemiacetal form available. Okay, it is naturally found to be dextrorotatory. It is an invert sugar. I told you the definition of invert sugar before. It is an invert sugar in aqueous solution. Next, it no mutarotation is observed. It does not show mutarotation. Okay, so this is about sucrose. Okay, please check it out quickly. If you have a doubt, you can ask me. Let's talk about the next sugar, which is maltose. Maltose is basically a glycosidic linkage between carbon 1 of alpha glucose and carbon 4 of again alpha glucose. So we need to take two alpha glucose here. So you can see this is the Haworth projection for alpha glucose and this is the Haworth projection for alpha glucose. All I need to do is make a connection between 1 and 4 carbon. Okay. You can see 1 and 4 carbon. If at all we establish a bond here between O and H here. So that will become an O linkage here. So this yellow color part which I have written, now this has become acetal form. So can I say that this carbon have now become acetal while this carbon is still hemiacetal. So please check. So hemiacetal is still intact, which means unlike sucrose, here we can say that the uh, uh, the hemiacetal nature is still existing. So it will still contain hemiacetal form. So if it is a hemiacetal form, that means it is reducing sugar. It is a reducing sugar, and it will also show mutarotation. Show mutarotation. Okay. Next one is lactose. Lactose is a glycosidic linkage of carbon 1 of beta galactose and carbon 4 of beta glucose. So this is beta galactose, the carbon 1 position, carbon 4 position of beta glucose. Now the connection between these two and that connection, if you notice, this is how the connection will establish and that is called as beta glycosidic linkage. Again, here there is an acetal form, but you can see here there is still an hemiacetal form. And because it is an hemiacetal form, these lines would be exactly same. These pointers will be exactly same for even uh, maltose. Okay, that is lactose. Lactose is also hemiacetal form, reducing sugar, and it shows mutarotation. Okay, so these three disaccharides you must know, guys. Okay, one is sucrose, second one is maltose, the third one is lactose. Okay, mainly learn about their connections, where exactly they have been made, and lastly polysaccharides. So if you take starch, okay, starch mainly contains two components. One is amylose, the other one is amylopectin. Amylose on one end is actually water soluble. 15 to 20% of that of the starch is made up of amylose. Amylopectin is water insoluble, and 80 to 85% of the general starch is made out of this amylopectin form. What is exactly amylose? See, amylose is a straight chain of maltose extension. That's it. You can see this is a maltose, right? This is maltose. Now imagine if this maltose keeps extending at carbon 1,4 position all throughout. So which means it gets polymerized on both ends here. So you can see C1, C4, C1, C4, C1, C4. It is just getting extended. So if you find this extension, then there is no hemiacetal left. Everything is acetal only. Okay. So all of them are glycosidic linkages. Here it is glycosidic, glycosidic, glycosidic linkage. And you can see, since it is all acetal form, it is non-reducing sugar, and also it does not show any mutarotation. Second thing, all of them are making only a straight chain type of a form. So in this case, amylose is a completely straight chain extension of carbon 1 and carbon 4. While amylopectin is a branch linkage between carbon 1 and carbon 6 somewhere in the amylose form. So suppose if this is an amylose form like this is another amylose form here. This is amylose and this is amylose. And somewhere in between, we have a carbon 1 and carbon 6 connection. Okay, carbon and carbon 6 connection. Here we are making an acetal form. And like that, this is the way it is. Somewhere here and somewhere here, somewhere here, somewhere here, somewhere here, like this. If this kind of connections keep establishing, this molecule is called as amylopectin. Okay, so amylopectin basically is an amylo structure only, but with a branching at certain positions between carbon 1 and carbon 6. Okay, right. Lastly, cellulose. What is cellulose? Cellulose is a polysaccharide made out of C1 and C4 connections of glucose. C1 and C4 of glucose. So these are also straight chain polymers. They are non-reducing and also does not show mutarotation. Does not show mutarotation. Okay. So here you can see from carbon 1, carbon 4 connection, carbon 1, carbon 4 connection, carbon 1, carbon 4 connection. Like a step up. It is like this. Like this, it will keep connecting between uh, beta glucoses form. So as the beta glucoses form grows like this and it goes n number of times, that is called cellulose form. Okay. Now glycogen mainly has amylopectin. That means almost we will say 99% of the bonds are only amylopectin form. So if they are all amylopectin form, then we call it as glycogen and also known as animal starch. Okay. So animal starch will usually have high amount of amylopectin connections. Okay, guys. So this is a theory that you need to know from carbohydrates. What are the connections and how to draw the Haworth projection? That's the main objective.